In this lecture, we're going to do example number 1 of ideal gases. Okay, so this is the example, and the example consists in the following. Let's call this example number 1. To understand this example, let's assume that we have a tank. Okay, so this is a tank. The tank, we want to know what is the total weight of the tank. This is what we would like to know. What is known in the problem is that the total volume is 1 feet cube. The gauge pressure is 50 psi. The temperature inside the tank is 70 Fahrenheit. Okay, so when we start this problem, the first thing we need to know is we need to find what the weight is. This is what we are looking for. We know the weight is equal to mass times gravitational acceleration. We know from here that mass, we know that we know that your density is equal to mass over volume. This dash is referred as volume. And then from here, I can solve for mass. Mass is equal to rho times volume. Okay, so if I take this and I plug it inside here, I get W is equal to rho times volume times G. Okay, now I would like to know, so in the problem now, I know my volume is given here. My volume is given. I know my G. We know what the G is. G is 32 feet second squared. But I don't know what my rho is. Okay, so we need to find the rho. In order to find the rho, what we can do is we can use our ideal gas law. We can use our ideal gas law that says P is equal to rho times RT, comes from our class. And then from here, since I'm interested in my rho, because in my problem, I know my pressure, this is a constant, I know my temperature. So I can solve for rho. Now my rho is equal to P times RT. Okay, so my W, my weight, becomes mass times G, rho times density times volume times gravitational constant, and this becomes pressure times R times temperature V times G. Okay, so let's start finding what the P is. You have to watch out because for a gauge, when you talk about a gauge, when you talk about the pressure gauge, the gauges, when they read the pressure, that basically you have your actual pressure, and then you have what you call the reference pressure. And the gauge is what will give you is a delta P. So what you know is that your delta P is nothing else than your actual pressure minus your static pressure. So if I want the P will be delta P plus my P sub 0. And that will give me I know that this is 50 psi, and the static air pressure for air is 14.7 psi. Okay, so from here, this is equal to 64.7 psi. Okay, we need to, for this problem, we need to work everything in pounds. So we need to convert 64.7 pound force inches squared. This is same as psi. Need to multiply that 144 inches squared is in 1 feet squared. That will give you 64.7144 pound force feet squared. Another thing I need to know is what's the temperature. Now, the temperature conversion, everything happens in Rankine because your constant, the gas constant R is given in Rankine, and the conversion is done by adding 460 to this. If I add 460, that would give me 530 Rankine. Okay, so this is the conversion to Rankine. So I have this, and I can calculate what my rho is. Now my rho RT would be 64.7 times 144. That is your P. Comes from here. Sorry. This is P. And then your gas constant is 1716 for air, multiplied by the temperature 530. That would give you 0.0102 slugs over feet cube. Okay, so then from here, I find that my weight is rho times volume times g is equal to 0.0102, and the volume is 1, gravitational constant 32.2, and that would give you 0.32844 pound force. Okay. Now, another concept that is very often used in these problems is the true gas. Okay, so for the case for true gas, for a true gas law, many times we call this or the non-ideal gas law. All we have to do is you have N RT, and you multiply this by a compressibility factor, Z. Okay, this is a gas compressibility factor. Okay, and the gas compressibility factor is nothing else than comes from this table. Okay, it comes from this table, and you can see that in our particular problem is 530. The temperature was 530. So it's somewhere here, it's close to this number, and the pressure was 64.7. So it's somewhere here. So I would say that a number is somehow close to this number. So you see that your compressibility factor for this particular problem is about 0.991. You can do linear interpolation if you want to be exact, but you can see the value between 60 and 80 is still the same number. The value might be it might be 990, and you're going up. So if you wanted, you could say this is anywhere between point 90, 0.99, or maybe even 0.90. You could sorry, 0.80, 0.98. It could be somewhere in between these values, even 97. You can do a linear interpolation between these numbers. And how you do linear interpolation? You take 450. This is the number that you're looking for, and this is the number that you have. This is 0.990. This is 0.955, and this is the number you want. Okay, and the linear interpolation is done as follows. So you use these 2 points where you can find a slope. So you will find a slope, your y, and then you can say a slope would be 0.99 minus 0.955 divided by 540, 450 times x and plus a slope. Okay. Okay. So this number will give you y is equal to 0.0003888889 x plus b. To find your slope, use any of these values. Let's say I want to use the last one just to use a value there. So we're going to say the answer of this will be 0.99. This will be a y. I'm using this y. This is my x. And then this will give you 0.0003888889 multiplied by this value, 540 plus b. Now you can solve for b, and by solving b is equal to 0.78. Okay, so now I have my equation. My equation is 0.00388889 times x plus 0.78. Now I can use a linear interpolation between these two numbers, and given the fact that my x is this value and this is the value I'm trying to look for, I can plug this value there and I can solve for y. And that will give you the following value. Okay. That gives you 0.9861, which is in essence very close to 0.99 if you wanted to keep that. But if you wanted to be exact, this is how you would do it. Okay, so this completes example number 1 of ideal gases.